And once we get started, of course, people on Zoom, please mute your microphone unless you have to ask a question.
And let's see here. The YouTube stream is live.
All right, everyone. Welcome to Mitch Dorrell's PhD defense. We've got two modes of delivery, one over Zoom, one over YouTube. If you're on YouTube and you want to ask questions, you can ask them in the comments section. And if you're on Zoom and you'd like to ask a question, please just kind of raise your hand or wave or wag your fingers at me or something. The public portion will probably end around noon, and then we'll switch to a private feed for the committee-only portion. I already asked everyone to mute. Okay. So the committee consists of myself, Alex Sote, who just introduced himself to the rest of the committee, at the NIH, Norm Wagner, chemical engineering here at UD, Sandeep Patel, chemistry here at UD, and Carl Unruh, physics in UD, and myself, Ed Lyman, physics, University of Delaware. So Mitch started at UD in the fall of 2013. He joined my research group in the summer of 2014. A couple of years later, in the fall 2016, he moved to DC to work at the NIH with Alex, funded by an intramural NIH fellowship. Mitch has published his first paper earlier this year in Journal of Chemical Theory and Computation on the work he'll present today. And another paper has been reviewed glowingly at the Chemistry and Physics of Lipids, and a third manuscript is to be submitted soon. And all of this is covered in the talk today. So without wasting any more time, I'll turn the floor over to Mitch. Mitch, please.
Okay. So today's discussion, I want to start with a brief introduction of cell membrane biochemistry and molecular dynamics simulations. And then I'll go over the basics of neutron scattering, the supporting mathematics for it, and also the existing technique that is typically used for the types of applications I'm going to discuss today. In section 3, then I will start to introduce the new methods that I've developed over the past few years, and also validate them against some proofs of concept. And then in section 4, I will be introducing a technique that is used to incorporate the effects of curvature into the scattering intensity results of a planar membrane. Finally, in section 5 of this talk, I will be going over a practical scientific application where we actually make some use of all of these new techniques that I've discussed by that point. So to begin, cells are the fundamental unit of life. And in my opinion, the most important organelle inside of a cell is its cell membrane. The cell membrane serves as the boundary between the inside world and the outside world for that cell. All interaction between a cell and its environment must pass through the cell membrane. Compositionally speaking, the cell membrane is very complex. There are countless types of proteins and carbohydrates embedded within the membrane itself, but the underlying structure is a lipid bilayer. The lipid bilayer consists of 2 leaflets, where shown here in the image as the red balls with the yellow tails. There are 2 leaflets of oriented lipids. The head groups are the orange balls, and the tail groups are those yellow lines hanging from them. There are hundreds of different kinds of lipids, so not all of them have 2 tails, but the head group with 2 tails is a pretty typical example. It's a very popular type that is in our cell membranes. To study the mechanics, though, we need to simplify this diversity to a reduced model that we can study in more detail. So we choose just a couple lipids to simplify the model. And we want to make sure we capture some of the most important aspects of the lipids in the membrane. So for one, the lipids we choose have phosphatidylcholine, or PC head groups. That's just a relatively popular head group. A very important characteristic of the lipids, though, are their tails. Tails can vary in length, as shown in the difference between DPPC and DSPC, but they can also vary in their saturation. where DOPC has an unsaturation in both tails, or POPC has one unsaturation in one tail. So in order to capture that diversity, in our model membranes, we will typically choose one saturated lipid and one unsaturated lipid. Finally, despite the hundreds or even thousands of different types of lipids present in mammalian cells, 30% of all of those lipids are exactly cholesterol. So that indicates to us that cholesterol must be a critically important lipid in our cell membranes. So for our model membranes, we will also make sure that cholesterol is one of our three components. So then you might want to ask yourself, what happens when you make a mixture of an unsaturated lipid, a saturated lipid, and cholesterol? Well, the result is a pretty interesting phase diagram. On the right here is a ternary phase diagram that represents all the different possible combinations of three components. The way these diagrams are read are essentially that as you approach one corner of the diagram, you increase the concentration of that component. So each corner itself is 100% of that component, and the middle of the triangle is a 33-33-33 mixture. For the membranes that we are interested in, as I said, a physiological mammalian cell membrane often has about 30% cholesterol in it. So those membranes would fall along this line here. Notice that the majority of that line is contained inside a two-phase coexistence region. When we build a membrane of a composition inside that region, it will demix along the tie lines to either the left side or to both the left side and the right side of this two-phase coexistence region. So when we make a membrane inside in perhaps this composition right here, it will demix into a liquid disordered phase and a liquid ordered phase. We call them the liquid disordered and liquid ordered phases due to the tail behaviors in those regions. The easiest way to see the reason why we call it that is using these images on the right. Essentially, in the liquid disordered phase, the tails are very disordered, and as seen by the squiggly blue lines, they're going everywhere. They're tangled, they're kinked, they're twisted. They're very, very disordered tails, as opposed to the liquid ordered phase, where the extra saturations help drive a more linear arrangement of the tail groups, allowing the lipids to pack a little tighter and creating a slightly thicker membrane as a whole. To seek a deeper understanding of these two phases, we turn to molecular dynamics. In a molecular dynamics simulation, essentially what we do is we put a few 100,000 atoms in a box and we evaluate classical Newtonian dynamics using a few phenomenological potentials as shown on the slides here. We do not model the quantum mechanics, and we do not allow bonds to break. So this is definitely a limited simulation. It's definitely a very classical approximation, but this classical approximation has been tuned to reproduce the critical behaviors of these lipids in the membranes. It's also been tuned for speed to allow us to accumulate enough simulation time in order to be able to observe the effects we want to observe. Another critical aspect of molecular dynamics simulations is periodic boundary conditions. When an atom walks off one side of the simulation box, it automatically appears on the other side. And what that means is that these atoms will never see any hard boundary in the simulation. From the atom's perspective, it lives in an infinite plane of membrane, so it will never see a specific finite boundary. So that will become relevant in a little bit later on. When we run simulations of the liquid ordered and liquid disordered phases, a lot of things come out as we expected. A lot of the experimental, or most of the experimental observables, such as membrane thickness, area per lipid, et cetera, are reproduced. But there was an interesting surprise from our simulation of the liquid ordered phase. This is a top-down view of a liquid ordered phase simulation. The yellow dots represent the centers of masses of cholesterol. The red and blue dots represent the centers of masses of the lipid tail chains. So that's one dot per tail chain, which means 2 dots per lipid for the red and blue. The red dots are the saturated lipid tails, and the blue dots are the unsaturated lipid tails. The interesting thing to observe here is this hexagonal packing of the saturated lipid tails that we're seeing. This is a liquid phase. The motions of these lipids are still very fluid. So while we see this packing, it is a transient packing, although at any given moment, there are these large regions of hexagonal packing present. This is what we would classify as a lateral structure, or in some cases, a lateral substructure. This lateral structure means that it is a structural variation that we're seeing in the plane of the membrane, as opposed to a transverse variation that we see moving through the plane of the membrane, such as from the head groups to the hydrocarbon region. These lateral structures can be extremely important. Some proteins are very sensitive to their local lipid environment. So if a protein is in a region that is locally and surrounded with hexagonally packed saturated tails, it may behave very differently from if that same protein was in a region surrounded by more disordered, more fluid environments. Unfortunately, since as you can see with the scale of the simulation, this is only a 10 nanometer box along one side. The length scales of these hexagonal clusters are far too small to be observed using optical or fluorescence microscopy. So instead, we turn to small angle neutron scattering experiments. In small angle neutron scattering, a beam of neutrons emanates from a reactor or a spallation source. It impacts our sample and is deflected off downstream toward a detector. The detector records the intensity pattern of the neutron waves. Now, this is a non-imaging technique. The pattern that's revealed on the detector is not a snapshot photograph of the structure present in the sample. Instead, locations on the detector represent the scattering vectors Q. The scattering vectors correlate to length scales and directions within the sample. So, for example, lots of atoms spaced exactly 4 nanometers apart may induce a strong signal at Q equals 2 pi over 4 nanometers. In our application, vesicles, which are bilayer spheres, essentially, vesicles in solution are our sample, and the incoming neutron beam, when it scatters off of these vesicles, the neutrons impact the vesicles at essentially a random angle. You don't know how the vesicles are going to be positioned relative to the incoming neutron, so the direction of the neutron relative to the bilayer normal is effectively completely random. This ends up randomizing the directional information in Q, but the magnitude is preserved, resulting in a pattern of rings on the detector. The intensity, since the intensity appears as rings, it's conventional to measure just the intensity radially from the center of the detector, and then we would plot that just as a function of the magnitude of the scattering vector, not the direction. Before I move on, I want to go over just a couple of critical differences between neutron scattering and X-ray scattering. Specifically, X-rays scatter from electron clouds, so heavier atoms with more electrons will scatter more strongly. This means that in X-ray scattering experiments, small atoms like hydrogen are effectively invisible. You'll see on the next slide that neutron works a little bit differently. With neutron scattering, neutrons scatter using the residual strong force. The residual strong force is a quantum mechanical interaction that is very hard to predict, but it is consistent. So hydrogen atoms can be said to scatter more or less the same way as other hydrogen atoms. That means that we can empirically determine the scattering behavior of a hydrogen atom and tabulate it. The scattering behaviors of atoms are typically tabulated using the scattering lengths. For neutron scattering, the scattering length is an abstract representation of the scattering behavior. Unlike with X-ray scattering and with hard sphere scattering, the scattering length does not correspond to a physical length scale. So while a negative scattering length wouldn't necessarily make sense for a classical scattering application, it's completely fine here because it's just an abstract characterization. In this case, the minus sign indicates that the scattered wave from the hydrogen will be inverted in phase relative to the scattering phases of most other atoms. The other thing to notice is compared to the issue with X-ray scattering, where hydrogen atoms are generally invisible, in neutron scattering, notice that all of the different types of atoms shown here, the atoms that are popular in organic samples, they all have scattering lengths roughly between 1 and 10. Those similar magnitudes means that this neutron scattering is sensitive to hydrogen positions, unlike X-ray scattering. Furthermore, the difference between hydrogen and deuterium gives us some extra flexibility. Hydrogen and deuterium, as two different isotopes of the same element, have very similar electron clouds. Their chemical behavior, thus, is very similar. But their difference in scattering behavior means that we can substitute one for the other without significantly affecting our chemistry. Did we just lose somebody? I hope not. Unfortunately, I can't tell whether somebody turned off their video or whether they've actually fallen out of the...
It said Alex went into the waiting room, but I just pushed a button to let him back in.
Okay, all right.
Thanks.
That actually reminds me, I wanted to lock this room so that we don't get any strangers. There we go. But I will turn off the meeting room so that you guys can come back in more easily. Okay. All right, sorry about that. Okay, so in regards to swapping hydrogens for deuteriums, one place where we often do that is in lipid tails. We can swap the white hydrogens shown on the left as in the proteated DPPC for deuteriums indicated in yellow in the deuterated DPPC. Both of these lipids are easily available from commercial vendors like Avanti Lipids. Both, when we make this substitution, though, we are dramatically changing the scattering properties of the hydrophobic region of the membrane. The scattering signal that is proportional to differences in scattering length density between different regions. So if adjacent volumes have the same density, the boundary between them becomes invisible. This ability to tune the density then can be used to then enhance or suppress signal from certain structures at the expense of others. Once we build our membrane and we put it into the sample, the next question you might ask is, what does the scattering intensity from a membrane often look like? Well, membranes have a lot of different structures in them. There's principally there's the thickness of the membrane. That's of course a very strongly correlated structure, but there's also a lot of other structures present as well. For example, interlipid distances, undulations, many others. There are lots of length scales present in the membrane. All those different length scales end up contributing to many different structural signatures that all get summed together into our scattering intensity graph. That means that when you look at the scattering intensity graph, it's very difficult to look at the graph and say, okay, this feature right here corresponds to this specific structure. That means the one exception to that is the vesicle or the membrane thickness. Membrane thickness can be related to the positions of the major crests in our scattering plots. But beyond that, it is very difficult to observe finer structural details by directly interpreting this type of graph. So instead, what we do is we take our simulations and try to predict our scattering intensity from those simulations to see how that scattering intensity compares to an experimental membrane. To make those predictions, we start with some basic scattering expressions. Typically, your typical scattering expressions like these can be found on the first pages of any scattering textbook. The scattering intensity is related to the square of the scattering amplitude. I should note that the scattering intensity and the scattering amplitude in these expressions is given as a function of the vector q. So these are full three-dimensional intensities. The scattering intensity is related to the square of the scattering amplitude, and scattering amplitude can be thought of as just the sum of all of the scattered neutron waves measured at the detector. Each wave gets a phase related to the position of the atom in the sample, and gets an amplitude related to the scattering strength of that particular atom or the scattering length of that particular atom. Another way to represent this scattering intensity is in a continuum form. Instead of representing each particle individually, you can represent it as a continuum region that you are then integrating over instead of summing over the individual particles. These two forms can be related by describing the density function of the particles using a Dirac delta function. These squared forms aren't always the most useful, however. Sometimes we want to be able to consider the scattering between different regions of the membrane independently. And with these squared forms, that's difficult to do because the sum of a square is not the same as the square of a sum. So what we can do, though, is we can expand these squares in the form of these expressions down here. Essentially what we do is in each expression, we change the summation or integration variable a little bit so that we can write it as a double sum and a double integral. But mathematically, these are perfectly equivalent to the squared expressions above. We will make use of both of these forms later. There's one additional form that we will be using, though, and that is that is related to the fact that these expressions are in terms of the vector Q, but as I've stated earlier, in our specific samples, we won't have any directional information. That means that we will always have to orientationally average these expressions. So the final version that we will be discussing is the Debye scattering equation. The Debye scattering equation essentially is just the orientationally averaged version of the equation was on the previous slide. One of the extra benefits of the Debye scattering equation is that those exponential phases end up being replaced by a sine function. That means that we don't have to worry about the complex numbers anymore. These expressions are strictly real, which facilitates numerical computation in some ways. So we have a mathematical expression now for the scattering of a system. What happens if we directly apply this to a simulation? Well, if you just plug in the simulation atoms' positions and identities into a scattering expression like this, you won't get the right result. The reason is that the reason has to do with the periodic boundaries of the simulation. In the simulation, while the simulation itself doesn't experience the boundaries, the way the simulation is stored in the computer, there is a boundary. All the atoms are located within a certain rectangular volume. Outside of that volume, there are no atoms defined. So if you try to scatter from this using a normal scattering expression, you are effectively scattering from a cube of atoms floating in a space of vacuum. When you do it like that, the scattering length density variation between something and nothing dwarfs all the scattering length density variations within the sample. And that means that you essentially get the scattering intensity of an isolated cube. That is not what we're looking for. That is not useful to us. So we have to identify some way to fill in the space around these cells. The conventional approach is to use lateral averaging. In the lateral average approach, the way it works is you slice the system up into individual layers and then compute the scattering length density of each layer independently. The average scattering length density of each layer then can be thought of or can be put together to form a one-dimensional scattering length profile. At this point, you have a scattering length density profile, a beta of R, so to speak, but there is no X and Y dependence. It depends strictly on Z. So one way to visualize that would be to use the image on the right, where the foreground quadrant has been omitted just so that you can see the cross section here. When you try to scatter from this type of situation, this is something that is very doable. This is a scattering that you can compute. The expression that you start with is the continuum model squared expression, and when you plug in the details for this, you end up getting a couple of delta functions times the Fourier transform of the laterally averaged scattering intensity, or scattering length density. So then when you orientationally average that, everything simplifies down and you get this nice expression at the bottom. This expression is very similar to those used in neutron reflectometry because it functions effectively the same way. This expression gives you the scattering intensity contribution from all the transverse structure of the membrane, which is the same types of structures observed in a neutron reflectometry experiment. However, it will necessarily miss all lateral structure. Any hexagonal packing that might be present in this membrane will not contribute to the scattering intensity because the first step in preparing this method is to average everything in the XY plane. As soon as you average over it, you've lost all that lateral structure information. So if you are trying to scatter from a membrane where lateral structure is important, you need to do something a little bit different. The next thing you might think is, why not replicate it? Replicating is pretty elegant mathematically. Uh, if we consider the scattering amplitude of a single cell, not the intensity, but just the amplitude, it's given by the sum as we discussed earlier. If we consider the scattering amplitude of a few replicated cells, each replication only introduces a displacement into the position of the atoms. This allows us to effectively factor out all of the scattering length or scattering amplitude of the original cell. When you factor that out, you can rewrite it like this. So here we have this is still the scattering amplitude. This part is the scattering amplitude of the original cell, and this part is a scaling factor that accounts for the phase differences introduced in each of the replications. So you, in the example shown here, there will be 4 terms in this sum. We can, for the time being, we can drop the scattering amplitude of a single cell and only consider that scaling term there, that scaling factor. Explicitly written out for the four images, it would look something like this. Replicating the cell in this manner has some critical issues. The main one being that while replicating the cell does increase the amount of scattering volume, for example, it increases by a factor of 4 here, while comparatively reducing the amount of boundary with vacuum. In a sense here, we've increased the scattering volume by 4, but the boundary only by 2. So you can imagine if we took this even farther and farther, we could further increase the ratio of scattering volume to boundary. That works in the sense that it gives you better scattering signal and reduces the influence of the discontinuities with vacuum. However, the problem is that the more cells you have, when you go to orientationally average this, the more orientations you have to use to appropriately converge the orientational average to the converged result. Therefore, in order to compute this accurately, you have to replicate it many times and then do a completely unreasonable number of orientational samples in order to get a converged result. In the end, it's not a computationally tractable problem. So instead, we took an analytical approach to try to evaluate this in a more direct manner. If we let the number of replications extend to infinity, we get a double infinite sum as shown here. I've expanded the dot product to show the dependence of this parameter on the box sizes explicitly. This sum is this double sum has the same form. It's that same prefactor, except now this gives you the scattering. This is the scattering amplitude modification for an infinite system. However, while these types of sums could normally be represented by a Dirac delta function, the sum over such an exponential can be evaluated to Dirac delta function. That's not okay in this case. This is the scattering. This is the prefactor against the scattering amplitude and not the scattering intensity. If you were to take this and square it, and you had converted it to Dirac delta functions, then you are squaring your Dirac delta function. It is okay to multiply a delta function in x by a delta function in y, but it is not okay to multiply a delta function in x by another delta function in x. That is a mathematically undefined operation. As such, you have to evaluate this in its squared form first, and then consider the delta behaviors of that squared form instead of considering them before you square it. If you square it and go to evaluate those behaviors, you get an expression like this. I just skipped about a year of mathematics in the click of a mouse. The consequence of this is you end up with these the Dirac delta behavior ends up falling into these two functions on the right here. These functions are called Dirac combs. Effectively, they represent a periodic chain of delta functions evenly spaced. The spacing of that delta of the chain is given by the parameter of the Dirac comb here. It's called a comb by analogy to the fact that a linear arrangement of spikes sort of looks like a hair comb. So to continue that analogy, we will call the product of two combs because the product of the two combs will end up forming a grid in two-dimensional space of these Dirac delta functions, we will call that product a Dirac brush because it will sort of look like a hairbrush. When we so this ends up being the prefactor against, considering that the square has been involved now, this is the prefactor against the scattering intensity. When you orientationally average it, your final result ends up looking like this. The mathematics behind this is pretty complex, and all the details are available in my dissertation. I'd encourage you to reference that for the careful details. But to give just a broad overview of what this is doing, this is the orientational average is sampling a subset of Q values of the magnitude that you want. So normally when you orientationally average over all different directions with over a unit cell with this, or over a unit sphere with a sphere's radius equal to the magnitude that you're trying to compute. In this case, though, while the radius of the sphere is still constrained to the magnitude that you're seeking, such as the magnitude of Q, the directions that you sample are only the directions where the X and Y components of the Q vector are compatible with the Dirac brush. So this ends up being a sum over those compatible QXs and QYs, and then the Z value is a continuous variable. So the Z value is whatever it needs to be to give you the to put that those X and Y values on the integration sphere. Fortunately, this ends up reducing the number of values that you have to integrate over, and being able to do a direct sum like this means that this is a fairly efficient thing to compute. It's this algorithm can be run practically on a laptop in a very reasonable period of time. Unfortunately, though, this perfectly models the periodicity of your simulation, and the periodicity of your simulation is not physical. In your simulation, each water atom, for example, water is in bulk water, the structure of the bulk water is not what you're looking for, but each water atom will see itself a distance L away, and then another distance 2L away, and another distance 3L away. That means that essentially what we've done by considering the simulation exactly is we've computed the scattering of a bilayer membrane crystal, and the scattering intensities of crystals have Bragg peaks. So we will expect to see periodic artifacts in the scattering intensity when we use this method. To avoid those artifacts, we use a mean field approach. In this mean field approach, the way it works is we consider the scattering from each atom independently. When you park your consideration on a specific atom, you then consider a cylinder around that atom where that particle scatters fully with full detail, with full particle-particle interactions with all other particles in that cylinder. Outside of that cylinder, you consider the interactions between the particle and a continuum model representing, computed using the laterally averaged scattering length densities, like I said, outside of the cutoff. This means that the particles will see all the detail they need to see inside the cutoff, but outside the cutoff, the only structure they'll see is the transverse structure, which does hold up at long range. All of the long range all the long range lateral structure, such as that given by the periodic nature of the simulation, is hidden by these lateral averaging in this region. Due to the nature of taking the full particulate considerations in near field while using the Fourier transform laterally averaged approximation in the far field, we call this the particle far field transform method, or PFT. So to discuss this mathematically, we break up into, I'm skipping a thing. To discuss this mathematically, we start with the Debye scattering equation again, because that relates the total scattering against the product of the scattering length density at the point you're considering and the scattering length density at a radius around the point you're considering. So this is a particularly compatible form to use with our cutoff. When we actually plug the type of breakdown into this, separating the the different regions from each other, we end up having this expression with 4 terms. These 4 terms correspond to the different types of interactions. And even term 1 corresponds to the interactions between the simulation box and the rest of the infinite bilayer. This is in term 1, there are 2 subterms, one considering the particular interactions and one considering the continuum interactions. But both of that is term 1. Because of the way that the system is broken down and because we're using the Debye scattering method, we also have to consider the infinite solvent background outside of our simulation box as well. The term 2 here relates to, or describes the scattering between the simulation box, the membrane in the simulation box, and the infinite solvent background, while term 3 is the scattering between a single box of solvent and the infinite bilayer. The difference between them is pretty subtle, and in fact, these 2 terms end up being equivalent, but I encourage you to look at the full derivation in the dissertation for more details about that. Finally, the solvent also scatters against itself, and that is represented by term 4 here. When you plug in the different continuum and particulate representations for beta, these expressions end up being evaluated to look like this, which is mathematically very complicated. But the important thing to notice here is that it is available in more or less closed form. And it is something that can be, it's not an iterative approach. It can be computed directly, which is good for the efficiency. Unfortunately, it's not as good as the Dirac comb method or the Dirac brush method is. This, in order to run in a computationally practical way, you usually want to run it on a small cluster at least. So we have introduced 2 methods for discussing or for computing the scattering intensity of a simulated bilayer. Now I'm going to validate them. To validate them, we created 4 simulations as test cases. The difference between these 4 simulations is the identity of the solvating lipid, the blue lipids in this case. The 4 simulations have different quantities of unsaturations in the tails of those blue lipids. These first 3 have basically, the first simulation has no unsaturations in it, so the red and blue lipids are actually the same. Of course, that will evenly mix. But in the last case, the unsaturated lipid has 3 unsaturations in each tail. And the contrast between having 3 unsaturations in the blue tails and no unsaturations in the red tails means that in that 4th simulation, the lipids completely demix and you get a well-resolved lateral structure appearing in that simulation. So the next step that we did is, while we simulated the dynamics using the appropriate identities of the lipids, when we compute the scattering intensities of these simulations, we redefine all of the blue lipids as being identical in all the different simulations. The reason we do that is we don't want to see the difference in the scattering strength of DFPC against DPPC, for example. Instead, we want to see the contribution of the lateral structure to the scattering intensity. So we essentially fix the transverse scattering behavior of these simulations by setting the scattering lengths of all the blue lipids to be equivalent. When we run our new methods on these cases, these are the results we get. First, I want to start with the laterally average result. This is the existing method. This is what was available before the research that I've published. With the laterally averaged method, you cannot reliably distinguish between those 4 simulations. The height of that crest varies a little bit, but in isolation, without anything to compare it to, you can't use that to extract much information about the structure in the membrane. However, using both the Dirac brush method or the PF method, you'll see one curve pulls away from the other 3 at this low value of Q. That curve that's pulling away is the fully demixed DFPC curve. What's happening here is the laterally averaged method is not able to measure the scattering contribution from the lateral structure, but the Dirac brush and PF methods are able to capture that. That means that the difference between the Dirac brush and PF methods and the lateral average methods will substantially only be whether it's accounting for the lateral structure or not. As such, you can make the statement that the lifting of this valley floor is associated with the presence of lateral structure. If you were to look at these curves in isolation, you can still see the lateral structure by comparing the depth of this valley to the high Q plateau or the high Q asymptotic behavior. When structure is present, the valley is much shallower than the high Q region is, while when there's no appreciable structure present, the valley is approximately the same depth. The elephant in the room here is the periodic artifacts present in the direct brush model. Since they are so visually distracting, for the remainder of this talk, I'm going to be discussing mostly the method and drawing those curves. However, for computational purposes, these Bragg peaks, these periodicity artifacts are narrow enough that if you were to perform a least squares fit using these types of curves, the narrowness of these Bragg peaks means that they don't actually contribute much to the fit, and you can use these curves to get the same type of fitting information that you can use the curves for. So that plus the computational simplicity of the direct brush method gives you the main reasons to use the direct brush method, while the method definitely gives you better curves for direct comparison to experiment because they're visually much less distracting. At the cost of increased computational complexity and the requirement of choosing a cutoff that is appropriate to include all of your lateral structures, but not so large that it will start to incorporate periodic images. So with the two new methods introduced, the next thing I want to discuss is how we account for curvature. Typical membrane simulations are planar, but vesicles are curved. And as such, we have developed a method to modify the scattering behavior of a planar membrane in order to reproduce the scattering behavior of a vesicle or any other type of curved surface. The way we do it depends on a geometric interpretation of the flexing of these membranes. Essentially, what happens is that when you bend a membrane, the upper and lower leaflets bend independently. There's not a lot of sliding friction between the two membranes. So yes, their flexes can be considered independently of each other. Each leaflet bends around what's called a neutral surface. The neutral surface is illustrated using these dashed gray lines, and that is the surface where the area at that point is conserved under the flex. So the geometric argument can best be seen by considering what happens to the hydrocarbon regions as you flex these membranes, as you flex these leaflets. For the outer leaflet, when you flex it downward, the hydrocarbon region gets laterally compressed. That means that it gets transversely extended in order to conserve its volume. For the inner leaflet, when you flex the membrane, the hydrocarbon region gets laterally stretched, which means that it will get transversely compressed in order to conserve the volume. The overall effect then is that the inner leaflet gets thinner while the outer leaflet gets thicker, particularly their hydrocarbon regions. These distortions can be expressed mathematically, as is detailed in my dissertation, and those mathematical expressions can then be used to transform the scattering length density profile of a planar membrane in order to estimate the scattering length density profile of a curved membrane. The results look something like this. Here I show the scattering length density profile of a planar membrane that has been adjusted in such a way. The vesicle modeled here using a triangulated mesh occupies the midplane between the two leaflets. So this entire region out here is the outer leaflet, while this entire region in here is the inner leaflet. The midplane hasn't moved, but the hydrocarbon region has certainly changed in terms of its structural behavior. Changing the thicknesses of these leaflets and of the hydrocarbon regions in these leaflets changes the distances between structures in the membrane and thus changes the scattering behavior of the membrane as a whole. So curvature effects especially curvature effects like these ones, can be very important. We model the scattering intensity of an entire membrane by mapping the deformed scattering length density profile over a vesicle, and by choosing thousands of points on the triangulated mesh and mapping it at each of those points using the local curvature parameters to parameterize the scattering length density of profile that's being mapped there. The effect of that is that if you don't have something that's just a smooth sphere, and you have something with curvature deviations, those deviations will be reflected in the scattering length density profiles at those locations as well. Once you have a fully defined scattering length density profile at all points in space, you can sample it using a Monte Carlo approach to evaluate the scattering intensity over this entire system. For validation, we also simulated in addition to the planar simulations where we've applied these techniques, we've also simulated actual full vesicles of 13 nanometers and 18 nanometers. For the comparison to those vesicles, we created a mesh of those same sizes and performed the mapping so that we can compare apples to apples. The results are shown here. The original fully simulated vesicle is shown using the olive curves, and then the scattering intensity of the planar membrane that has been deformed using the curvature technique is shown using the violet curves. The main takeaway here is that for both the 18 nanometer vesicle and the 13 nanometer vesicle, we were able to reproduce the scattering successfully without necessarily having to simulate the full vesicle in itself. Simulating a planar bilayer is much more computationally efficient, and we can do that for a much longer period of time than we can do for a full vesicle. So this allows us to effectively get a vesicle's scattering behavior for a much cheaper computational cost. To put all these different new techniques together, we're going to search for the presence of this hexagonal packing of the saturated hydrocarbon tails in the liquid ordered phase. But in order to do this, the first thing we need to do is decide exactly what composition of liquid ordered phase we're going to use. In order to do that, we first consider deuteration. Using a 90% D2O solution and fully deuterating our DPPC tails and cholesterol, the idea here is that when the DOPC, which is proteated, separates out into the interstitial regions between these hexagonal phases, that will create a distinct region of different scattering behavior within the plane of the membrane. Furthermore, the solvent D2O substitution there helps us reduce the transverse scattering influence from just going from solvent to membrane to solvent. It's not a complete match, but we are approximately matching the scattering length density of the solvent to the membrane. This should allow us to highlight the presence of any hexagonal patches that form. But it's so we created a set of 9 different vesicles with different compositions along the LO-LD tie line, deliberately crossing the point where we expect the LO tie line endpoint to be, and evaluated the structures that you can see in the small angle neutron scattering at those different locations. The end result is that samples C and D showed the best structure visible using the neutron scattering, although we don't really have any way of interpreting that yet. But there was definitely structures visible in the scattering intensity plots there that were less visible in the other samples. The next question we need to ask is we need to make sure we are comfortably in the LO region. We don't want to risk the chance that we may accidentally have some liquid disorder phase separation in our membrane. We want an entire membrane of LO phase because we are only looking for the hexagonal packing in the LO phase. We don't want to complicate things by also including the contribution from LO-LD phase separation as well, because that would be another source of lateral structure. We only want to look at one lateral structure, which is the presence of hexagonal phases. So using small angle X-ray scattering, we built 5 different samples and found that the precise position of the liquid ordered phase boundary is between samples C and D here. So we choose sample C because it was comfortably in the region of ideal deuteration characteristics and also comfortably outside of the 2-phase coexistence region. The next consideration is that we know that the experimental system will have a distribution of vesicle sizes. We model this distribution using the Schultz distribution here, where R sub m is the average vesicle radius and z represents the width of the distribution. For those who prefer to measure things in terms of the polydispersity variable, z is directly related to the polydispersity variable as well, of course, through the fact that this is the standard deviation of g of r. The vesicle size distribution then is used to inform the curvature considerations and essentially allows us to average. We take the curvature effects and average them over the different vesicle sizes according to this distribution to account for the dispersity of vesicle sizes in our that we anticipate in the experiment. When we put all of this together and we actually generate our scattering intensities using these techniques, these are the results we get. I'm including here a comparison between the laterally averaged techniques that were before my research and the technique that we have developed here. So as a reminder, the critical difference between the laterally averaged technique and the technique, the main difference in the way in the features they report is the presence of structure, of lateral structure. Transverse structure is modeled in both, but lateral structure is only modeled in P. So we'll model the structure from the hexagonal packing, but the lateral average techniques will not. Comparing the green curve to the blue curve, you can see that there is a difference just below Q equals 0.2 inverse angstroms. So is definitely seeing some structure there that the laterally average system is not. But neither one of these curves really fits the experimental data to make some bold claims about what we're seeing in the experiment. But we're not done yet. There's one extra consideration that we've made. We realize that different vesicles in our sample will have slightly varying compositions as well. Not every single vesicle will have, for example, exactly 63% DPPC. So to account for that, we ran simulations of 57 different compositions around the targeted liquid, the targeted liquid order composition. Of those 57 compositions, then, we ran a non-negative least squares fit to determine how each of those compositions contributes to the experimental scattering intensity. It's important to note that while we have 57 different things that we're fitting here, that we're fitting together, all of these are very similar compositions, and so they're all generating very, very similar scattering intensities. That means that the scattering intensities that we're using for the fits, they only differ in very small ways. So it's not a true 57 degrees of freedom here. That would be completely absurd. In fact, due to the non-negative least squares fit, only 3 to 4 of these different compositions are actually reported to contribute. And in the case of our fit, it ends up being these 3. Now, these 3, you might expect that they would surround the targeted liquid order composition, but keep in mind that the differences between these different simulations are very, very minor. So instead, it's better to think of these as just 57 different stochastic variations in the realm of the true liquid ordered phase identity, and so they will not necessarily average to give you the exact location there. They're too similar to get that type of information from it. So, final results. What do the scattering intensities look like? We're going to do a comparison again between laterally average and oops, this is the result. So here we have laterally average on the left in green and again on the right in blue. Once again, I forgot to mention it. I'm sorry. These experimental data is shown in red here. Again, since the difference between the laterally average and the curves is strictly with the presence of a lateral structure and whether we are accounting for that lateral structure, that means that the depth of that valley again is whether we model the lateral structure or not. Since which models the lateral structure fits that valley much better than the laterally average system does, we can conclude for the first time that yes, indeed, the experimental membranes of the liquid ordered phase at these compositions do in fact exhibit hexagonal packing of the tail chains of the saturated lipids. This is the first time that this has been shown, and this is the first time that this has been demonstrated for an experimental vesicle. So to wrap things up, just to recap, we introduced two new methods. We introduced the Dirac brush method, which is a mathematically exact method and which models the perfect periodicity of the simulated system, but has periodic artifacts. And then we also introduced the method which avoids the periodic artifacts by using a mean field approach, but still captures all of the local considerations, all of the local structures. We then introduced a curvature technique that allows us to add in the effects of curvature to a planar bilayer simulation in order to account for that in the intensity. And we use all these techniques together to compute the scattering intensity of the liquid ordered phase from the simulation and confirm that the hexagonal packing exhibited by the simulation does in fact appear in the experimental results. So with all of that said, I want to thank just a few people in particular, a few people that were especially important in getting me through this in my graduate program. First, I want to thank my advisors, Ed Lyman and Alex Sote. They've both been instrumental in helping me to develop my graduate studies and helping me get through all of this research and helping me get past my roadblocks. I also want to thank my experimental collaborator, Fred Heberly. He is the one who actually created our samples and put them in the neutron beams for us. And then I want to also thank my fellow group members. I have too many group members over the years to list them all on this slide, so I'm going to list specifically the ones that have that have taken time out of their day to contribute to my dissertation and defense. And those are Swapnil Baral, Kayla Sapp, and Andrew Bevan. Thank you guys very, very much for all of your assistance. Additionally, I want to thank my family, my mom and dad, and my siblings, Jill, Vince, and Sky. They have heard this presentation far too many times over the past several days, but they've definitely helped me tune things in. I also want to thank my friends. Again, too many friends to list, but the ones that have made specific contributions to my defense, my friend Breja, my friend Mike, and my friend Jason. Thank you guys very, very much for all of your help. And finally, also, I want to thank my girlfriend because you wouldn't believe what she's had to put up with over the past several days as I've been working on this dissertation, and even over the past several months as I've been writing things up. I have not been an easy person to live with, and so I thank her very, very much for putting up with me. So thank you all for your time. Thank you for listening. And at this point, I am happy to take questions.
Great. Thanks, Mitch. Alex and I also would like to thank Dee. So at this point, I'd like to open it up to non-committee members. We'll save our questions for the next session. But if anybody in the audience on YouTube would like to ask a question, you can type it in the box or you can send it to me via email. I didn't tell you my email. It'selyman, E-L-Y-M-A-N @udel.edu. But I'll take a look at the YouTube feed. And so if you put a question in their box, I can ask it. You got a couple of great jobs, awesome. Mitch, but no questions yet.
Okay. Cool.
I'll give you a few minutes.
I look over here and I see 35 concurrent viewers. Now, a couple of them are probably us, but that's a lot of people watching. So thank you everybody for tuning in. I do appreciate that. Thank you all for watching. Although I can't see you guys and I'm not communicating with you directly, your presence is definitely noted, and I definitely appreciate all of your support over the past few months and now especially. So,
any questions from the audience at all? Going once, going twice. Okay, sold. So, so Mitch, why don't you go ahead and shut down this feed, and we'll take a quick break, and then I'll start the second Zoom session for the committee. And if any of the committee members need it, just email me or text me. But you should have a link from me in your inbox.
All right.
Okay.
thank you everybody on YouTube. And just as a reminder to everybody, this stream will be available to play back later on after this session is closed. It might take a little bit of time to transcode, but it will be available to watch back again later. So thank you all for tuning in, and have a good rest of your day.
All right, Mitch, we'll see you in a few minutes.
See you all later.